Thank you for coming to my presentation, everyone. Today, I'm very happy to present our paper, Precise and Accurate Patch Present Test for Binaries. My name is Zhang. I'm a PhD student from UC Riverside, and my co-author, Zhang, is also my advisor. Okay, let's first take a look at the problem we want to solve in our paper. I can give you a short answer currently. Given an Android image, how can we decide a specific CVE has been patched? Obviously, this is an important problem, right? Because for attackers, they can try to exploit unpatched vulnerabilities. And for defenders, they must ensure that all the security patches has been propagated in time. So I will use a real-world example to explain our problem more clearly. We know that the Linux kernel itself is open source, right? And the Google's Android kernel, which is also based on the Linux kernel, is also open source. It's AOSP project. Okay, so how about the third-party vendors' Android kernel? They are also forked from the original AOSP project, but they have some modifications. And for these kernels, usually the vendors will only release some snapshots of their kernel source code occasionally, and these releases are usually with significant delay. So for most of the time, we can only get the Android kernel images in binary form for this vendor's kernel. So in this situation, if we find the security vulnerability and related patches in the mainstream Linux kernel or OSP project, how can we ensure that they are propagated to the vendor's kernel? And actually, this is not only for the Linux kernel or AOSP project. Basically, in any scenario where the open source components are reused in the closed source software, the same problem exists. We can ask whether the open source security patch has been applied in the binary. And this is the problem we want to solve in our paper. However, this problem is challenging. We have two challenges for it. The first one, this task is like you need to locate the needle in a changing haystack. On one hand, a security patch is like a small needle. It's small and subtle. For example, this security patch, it only changes an operator. And this patch, it only adds a small line, a single line in the original function. So they are both small and subtle. Furthermore, the haystack is changing. For example, this AOSP security patch has introduced a new line in the original function, right? And later, this security patch can be backported to vendor's kernel with different contexts. And then there can be other patches applying on the same function and changing the contexts. So all four versions are patched versions, but they all have different contexts. So this makes our problem much more difficult. The second challenge, the haystack we need to search a needle is a binary instead of the source code tree. This is also a difficult problem. So there exists some related work to this topic, but basically they cannot solve our problem. The first category of related work is source code level matching. Basically, this work will try to search a source code snippet in a target source code tree. Obviously, we need to deal with the binary, so this type of work cannot work. And the second category is the binary-to-binary matching. And they will try to search a binary instruction sequence in the target binary. However, the thing is that this work lacks knowledge about the needle itself. Remember that we need to search a needle in the haystack, but usually this type of work will compare two binary haystacks and give us a coarse-grained similarity score between the two binary haystacks. But we need to search for the needle. So only with the source code level patch change set information, we can get the best knowledge of the needle itself. Okay, here comes our solution. Our system is named Fiber, and basically it's motivated by human experts' behaviors when faced with the same problem. At a high level, we will first analyze all the change sets introduced by security patch, and we will pick out those most suitable change sets and try to translate them into binary level signatures, which can then be used to match in the target binary. And this way, we can correlate the source code level information and the binary level information and to develop accurate and precise patch present tests. Okay, so next I will detail our workflow from the patch change set analysis part. Let's first consider what a human will do in this situation. Imagine that currently you are given an open source security patch, and you are asked to locate it in the target binary. So what's your first thought? Well, a security patch can introduce multiple change sets in different functions and across multiple files. So very naturally, the first thing we need to do is to pick out those change sets which are obvious, unique, and representative. And then we can try to locate the change sets in a target binary. In our system, we consider several factors when picking out the change sets. The first factor we consider is uniqueness. For example, this security patch has introduced a new line in the function, and we must ensure that this new line only appears in the patched version. And if this line also appears in the unpatched version, maybe in a different position, then we will be unable to differentiate the patched and unpatched version solely based on this single line. And in this context, we must add some context lines around this change set to make it unique. And the second factor we consider is stability. As we mentioned previously, the context of the original function can be affected. So if we include too many source code lines in our change set, then our change set is unstable because it can be easily affected by other security patches or by other changing contexts. So we must ensure our change set is stable. And to do this, we want to keep our change set as small as possible. And usually, we will always start from a single line, and we only add context lines when necessary. And the third factor we consider is easy to recognize. For example, a security patch has introduced a new function call, right? And this function call is not inline. So this is almost a perfect change set. Why? Because we can easily locate it in the target binary by simply looking at the calling instruction and the calling name. It's very straightforward. And the security patch may also introduce some conditional statements, like this if statement. This is also a good change set. Why? Because this if statement will change both the syntax structure and the semantics at the binary level. It's also obvious. However, if a security patch has only introduces an assignment statement, this is not as good as the previous two cases because it will only change the semantics and the syntax structure will remain the same. So basically, in our system, we will try to rank all the change sets according to our domain knowledge. The goal is to pick out the most easy to recognize change sets. Okay, so now we have a set of proper change sets. And next, we need to translate them into a binary level signatures, which can be used to match in the target binary. So how can we do this? If we want to do this manually, what we will do? Let's still consider a small example. And this is our source code level change set. It's if statement and with two branches. So the first thing, very nature, is a syntax structure. Because syntax structure is very obvious. At the binary level, we can expect a conditional jump related to if statement. And we can expect two following basic blocks representing the two branches, true branch and false branch. And besides syntax, we also need to consider the semantics, which means for the condition used in the conditional jump node, the condition should be exactly the same as the source code level change set. It should be A bigger than 1. And the same thing for the true and false branches. So our system basically follows the same procedure. We will try to correlate both the syntax and semantics from the source code to the binary code. Okay, so to do this, our first step is to identify all the binary instructions that are related to the original source code change set. Fortunately, because we have the patch source code, our life is made much easier because we can compare this source code into binary, and the compiler will generate the debug information, which provides the mapping from the source code lines to the binary instructions. And in this example, we identify 4 binary instructions that are related to the source code change site. And these 4 binary instructions, they form a local control flow graph. The first node is a conditional jump. Second is a function invocation. So next, we need to consider semantics of this local control flow graph. For this purpose, we need to first identify all the root instructions within each basic block. So what are root instructions? Let's consider the first basic block. And the add instruction will calculate the sum of the x3 and x4 and store result in x0. And then the x0 will be compared to x2 in the CMP instruction. So in this example, the add instruction only produces some intermediate results, which will be consumed by the CMP instruction. And the CMP instruction has already captured all the semantics of the basic block. So we say the CMP instruction is a root instruction. Formally speaking, we define the root instruction as those instructions whose outputs will no longer be consumed by other instructions. And in practice, we identify all the root instructions by performing a basic block level data flow analysis. After we get a root instruction, we need to associate semantic formulas to each root instruction. Let's still consider the CMP instructions we identified previously. If we only look at this single instruction, its formula is like x0 bigger than x2. But if we also look at the preceding add instruction, we know that the x0 is actually a sum of x3 and x4. And if we look even further, we know that x3 comes from x0, and x4 comes from x1. So our formula becomes x0 plus x1 bigger than x2. So up to this point, we cannot transform our formula anymore because we have already reached the function entry point. So what does this formula mean at the source code level, where by the ARM64 calling convention, x0 is the first function parameter, x1 the second, x2 the third. So at the source code level, this means a plus b bigger than c. This way, we can correlate the semantics between the source code and the binary. Our system will extract all the semantic formulas by performing a function-level intra-procedure and under-constraint symbolic execution. OK, so now we have a binary signature, which is basically a local control flow graph. And every node contains a set of root instructions, and every root instruction is related to a semantic formula. So next, we need to match this binary signature in the target binary. How can we do this? Well, at first, we can consider some quick and easy to collect features. For example, the topology of the binary signature. And in this example, the topology is just 2 connected nodes. And we can also consider the root instruction types included in every node. So in this example, the first node should be a conditional jump. A second node should be a function invocation, and the calling name is bar. And by these quick features, we can already rapidly narrow down our search space in the target binary function. Just by these quick features, we have 2 candidate areas. And then we need to further do the comparison based on the semantic formulas. We need to extract semantic formulas for the candidate areas and compare them to the formulas of the original signature. And by the comparison, we can exclude one of these candidate areas. So only one matches. In this case, the binary signature has been successfully matched in the target binary. And we can see that the patch is present. OK, so to compare 2 formulas, basically we will first simplify the formulas by the Z3 solver, and then we perform a strict formula match. OK, so far I have covered the general workflow of our system, but there are some special and interesting cases. The first case, imagine that the patch has introduced a function call, and this function call is unique, which means it only appears in the patched version, and this function call is not inline, which means we can search it by looking at the calling instruction and the calling name. And in this situation, we don't need any semantic formulas. So we don't need symbol execution in this situation. Just a very simple calling existence test in the target. The second example, let's look at this security patch. It only changes one single parameter within a function call. So recall that previously we said to keep our change size stable, we will only start from a single line. But in this case, it's not even a single line. It's a single parameter. So in the binary signature generation and matching process, we will only include these instructions that are related to the single parameter, which makes our matching more accurate and stable. So we have other corner cases, but due to a time limit, I will not cover it currently. And if you are interested, you can refer to our paper for more details. Okay. So comes the evaluation part. And in the evaluation, we have crawled 107 security patches from the Android Security Bulletin. The time frame is from June 2016 and May 2017. We also collected 8 Android kernel images from 3 mainstream vendors. And basically, we try to test the patch presence of these patches in these Android kernel images. Let's first focus on the accuracy. And overall, we can say that our system have excellent accuracy. And on average, we have the 94% accuracy, and we don't have the false positives. So the false positive means that we wrongly believe the patch is present, but in fact, the patch is not there in the binary. This is dangerous, because this can mislead the developer to ignore a certain security patch. We do have some false negatives, and the false negatives means that we wrongly believe the patch is not there, but the patch is actually there. This requires extra time for the human experts to confirm, but anyway, it's secure. So we give detailed analysis of the root cause of the false negative in our paper, and you can refer to our paper for more details. And here I only want to introduce 2 root causes. The first one, the function inline. So recall that our binary signature is generated from the reference binary and source code. So if a callee function is inlined in the reference, but not in the target, our binary signature will fail to match. The second reason, the patch adaptation. If a patch is backported to another function, maybe the change site of the patch can be modified to suit the target function. So in this case, our binary signature will also fail to match. But anyway, its binary signatures are secure, and in the future, we try to resolve these false negative cases as our future work. Okay, then let's take a look at the performance. To be honest, our system is not as fast as previous binary to binary matching work, because we consider more expensive semantic features. But in exchange, we have better accuracy, and we believe our performance is still acceptable, because it's still much faster than the manual work. And besides, our system can be easily parallelized. And in our evaluation, we also identify many vulnerabilities which are not patched in the Android kernel images. If we analyze the time lag of these security patches, there are 2 security patches are not propagated to the Android kernel image after 1 month, and 5 after 2 months, 2 after even half a year, which is very amazing, right? But we believe that our system will help to avoid such cases in the future. Oh, by the way, some of these half-a-year security patch cases have been confirmed by the vendors. Okay. So here's the case study of our system. This CV is one of those half-a-year patch. So we can say the patch itself has introduced the single line. The single line is very small. It's just an assignment statement. And our signature is basically a basic block. And our semantic formula is to store this 0 value to a memory location. And the memory address is x0 plus an offset. And this x0, by the calling convention, is the first function parameter. In our case, it's a secf function parameter. And x0 plus an offset basically means the dereference of a field within the secf structure. So we match the binary level semantic with the source code level semantic in this case. Okay, about our implementation, we use Anger as our symbolic security engine, and we modified its internals. And our system has around 5,000 lines of Python code, and it's still under improvement, but we have open sourced it on the GitHub. If you are interested, please feel free to check out our implementation and leave us some feedbacks. Okay, that's basically all. Thank you.
Time for questions. To start this off, I'll ask a question. So, if a patch is applied in principle, so not exactly as it is created, but if it's applied in principle to do the same thing, does the system also detect that? So, say we don't really use the same. We don't create a new variable, but we just do something similar with the old variables. Does your system detect that?
Sorry, can you?
Sure. So if a patch is semantically applied, so it's applied in principle, but it's not really applied exactly as it is.
Okay.
Would your system detect something like that?
Okay. So I think it's basically very similar to the patch adaptation cases, right? A patch may be semantically similar, but on the syntax level, it may not be exactly the same. And in this case, we do encounter some difficulties in our matching. But basically, because we look at the semantic formulas, we think we can still deal with the part of these cases because we look at the semantic features instead of purely the syntax matching.
Looks like we have another question.
Okay. Hi, Phoebe Rouge, Federal Trade Commission. I'm curious, have you looked at, so like the Android patch level will say, okay, this was patched up to March 2017. Have you looked at a comparison, like seeing if the patches that you detect in the actual kernel image actually match with those dates? Because there's, it could be that they're just, because that date is, just set by the vendor, so have you sort of tried to compare that to see if there are discrepancies?
Sorry, kind of quite.
Yeah, sure. So like if if you go into your system information, you see that the Android is patched up to March 2017. So it should have all of your security patches up to that date, right? So the question is, have you thought about taking your methods and actually verifying that an actual binary kernel is patched as far as it says it is?
No, we haven't done that.
Okay.
I'm sorry.
Yeah.
We do have some anecdotal evidence. I mean,
okay.
Someone else actually published some reports saying that vendors sometimes do cheat the customers. Mm-hmm. They claim that the patch has been applied, but it's actually not. We haven't done that, but it's something we can do.
Yeah, that would be really cool.
Thanks.
Thanks.
Okay.